let's revisit the helium atom ground state. Now we know how to write it out properly. We want to examine the properties. So we know the proper way is to write down a 2x2 determinant. A state is 1s up, B state is 1s down. That's fine. Multiplying out, we have this. Or in our notation, up is alpha, down is beta, things like that. So actually this is 1s in real space, that is alpha theta phi, and then an up spin part. The second term will be 1s down, so another 1s, but it's the second electron, it is in the down state, okay? So this is the beginning of our discussion, what we call the wrong attempt. But a wrong attempt can be turned into a correct form by anti-symmetrize it. Linear combination with a minus sign. So this is now our correct form. These three forms are equivalent, all right? Now, for ground state, at the beginning in our mind is that we have two electrons both in the 1s spatial state. Okay, now that is 1, 0, 0 alpha theta phi. All right. So now we see we have one electron number 1 in 1s, electron number 2 in 1s. This side we have electron number 2 in 1s, electron number 1 in 1s. Now this product of terms appear in both terms, and they refer to the spatial, to the atomic 1s orbitals, okay, or 1s state, right? And that means we have this state has to do with a 1s wave function, okay, related to alpha, theta, and phi. Okay, do you follow me? So when we see phi, it has to do with something in the x, y, z, or alpha, theta, phi space with the nucleus at the center, all right? So now we see this common factor, we pull it out. Then the remaining term has to do with the spin only. The first term has to do with what we regard as electron number 1 is up, down is 2 is down, but the second term has to do with this, okay? And the wave function here deals with spin, has both possibility, this and that. All right. And if you read out the prefactor, you see that it's 1 minus 1 means equal probability. Okay. In quantum mechanics, you read out the coefficient square is the chance you find this or that, right? So this is a very interesting spin combination. We have two electrons, both spin half, therefore, that must be a two-spin wave function, okay? So remember, electron has spin half. We are adding spin half to spin half, angular momentum. We learn how to do it, at least we know the rule. Half with half, you get a total spin angular momentum. The quantum number can take on half minus half to half plus half. So 0 or 1, right? For 0, the ms can only be 0, so one state. For S equals 1, ms can be 1, 0, minus 1, 3 states. 2 spins, up, up, down, 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 up, down, 4 possibility. You add it up, you get 4 states, no more, no less, because they are only linear combinations. Okay, so do you follow my story? I'm repeating a story of adding 2 angular momentum. You follow that? I'm reminding you something. Okay, so now let me summarize this page. For the helium ground state, we know how to write it down properly. And then we realize one special property. It factorizes into 2 parts. One part only related to the spatial wave function, the 1s orbitals. The other part has to do with the spin of the 2 electrons. We call it the spin part. Okay? And now let's check the symmetry properties of the 2 parts. The overall ground state must be antisymmetric because it has 2 electrons, fermions. We notice that the spatial part that has to do with R1 theta 1 phi 1, R2 theta 2 phi 2, that is symmetric. Okay, do you see that? If I interchange R1 with R2, this whole thing does not change. Do you see that? Hello, hello? Okay, now, all right. Now, the whole thing is antisymmetric. Therefore, the spin part better be antisymmetric. And indeed it is, you see. If I interchange 1 and 2 in this whole thing, because of the minus sign in the middle, this whole thing will have a minus sign when I switch 1 with 2. Okay? Therefore, the product is antisymmetric. Wonderful. It should be because we started out with the right one. Okay? But now we see for 2 electron case, it turns out rather nicely. We can factorize into a spatial part and a spin part. Ground state, spatial part is symmetric, spin part is antisymmetric. Maybe for the excited state, could we have spatial part being antisymmetric and spin part being symmetric? The product is still legal. Okay, now that is why I picked this point up here. In fact, we will have that possibility in the excited state, but not in the ground state, excited state. Why? In the ground state, our picture is both electrons in 1s. There is the only thing you can write down. One in 1s, another in 1s. That is the only thing that you can write down. I highlighted there. We cannot construct anything else. And immediately you see the space part, you have no choice. It is symmetric, therefore you go with this part, the antisymmetric spin part. Okay, do you follow me? So I already mentioned everything on this page. What we learned in this, just write it down explicitly. We see that 2 electron wave function can be factorized, a spatial part and a spin part. Okay. Then it gives us more possibility. In the ground state, we see that this must be symmetric, this is antisymmetric. However, more generally, as long as this is antisymmetric, we obey the rule. So there are 2 possibilities. How about the spatial part antisymmetric and the spin part symmetric, or the other way around? both will be okay, all right? So in excited state, we will see that indeed, we have these two possibilities, and we have to check whether possibility number 1 or possibility number 2 has a lower energy. That is to say, which one is the first excited state? The answer to that question leads us to something very big in physics that hints at why on earth we have magnetic, ferromagnetic materials. Okay, so you see, tiny helium atom give us a lot of things. Tiny hydrogen atom give us most of quantum mechanics techniques and ideas, spin orbit interaction, for example. All right, so now let's inspect. Okay, we have seen this for our ground state, but for excited state, we may have one electron in 1s, another electron in 2s. Then the two spatial state will be A, B can be different. We could have antisymmetric spatial part. Okay, so that is the possibility. Okay, so now if it is ground state, we only have this symmetric spatial part. And that leads us to a discussion on the spin part. We look at this ground state situation, it is up down. Again, don't overstate what you know, right? We don't know which is up, which is down. That's the key point. Therefore, we better write down a linear combination of one is up, the other is down. If we only include this, we are lying. We don't know which one is which, so we cannot say number 1 is up, number 2 is down. We have to include linear combinations of two possibilities. In addition, we have to guarantee it is antisymmetric to go with the symmetric 1s, 1s spatial part. So we have no choice. That is the only choice. Okay? So we have seen that, and now we understand that we have no choice. That's the only thing that we can write down for antisymmetric situation. Okay, so, and together, the two arguments, in spatial part, this is the only thing we can write down. That enforces us to the spin part. This is the only thing we can write down. The product is the only thing that we can write down for the helium ground state. The helium ground state is unique. You don't see degenerate ground state. This is the unique single allowed ground state. Okay? And for that, we go back to the knowledge about adding 2 spin half. We call that adding 2 spin half could lead to total spin quantum number s equals 0 and s equals 1, so-called singlet and triplet state. By the very fact that we already argued, this ground state is unique, meaning there's only one. Immediately, we realize that it must be the s equals 0 state, right? Because the quantum number behind it, the so-called ms, the z component can only be 0. There's only one value. So this will be unique. There's no degeneracy behind it. Okay, so this is the argument, a lazy argument that I try to make, so that I will regard this combination up, down, minus down, up is the singlet state. Okay, so for possibility, we have taken out 1 in this particular form. All right, so follow me up to here. That is to say, helium atom, ground state. is a spin singlet. Okay, do you follow me? See ma? Okay. But we will not stop the discussion here, all right? Because we have the other three stages that we call spin triplet. It may be a good place here to find out what do the three triplet state refer to in terms of this up, up, down, down, and another possibility, up, down, plus, down, up. We have used it the -1. This is the singlet, but there could be a +1, okay, the plus sign, and that will be symmetric, all right? So here we conclude this is the spin singlet way, okay? We learned two spin half can add to a spin triplet and a spin singlet. This particular one is the spin triplet combination. In the vector model, just a model, okay, a lazy way to remember things, it is like you have a spin half, then you have another spin half. They always go now. You know this half means it is a cone, okay, and then the projection is up. You have another one spin half, the same length, but it lives in this lower cone. The projection Z component is always minus h bar over 2. That is what you call spin down. And these two things in a pictorial way, classical picture, it looks as if they are always opposite to each other, canceling out everything, and they live like this in their respective cone. So this is the picture of vector model depicting this spin singlet state. Okay, again, it is a classical picture to represent something very quantum. It has its limitation. So now, finally, let me remind you of what we have done so far is that we know how to write down the ground state wave function. Okay, so we know how to write it down. And now, last week, we learned how to handle the helium atom Hamiltonian and then try to approximate it into a single electron Hamiltonian so as we can solve for the 1s state. So with this, we can ask, what is the ground state energy? The ground state energy is the expectation value of this ground state with respect to the Hamiltonian of the helium atom. So you need to do an integral, again, 6 variable integral, because you have x, y, z here, x, y, z here, okay? So the TA has worked this one out for you in this week's exercise class. It can be done, okay, but rather involved. So in order to get the helium atom ground state, you need to do that. And you pick up the J integral, okay, the direct Coulomb integral. So I'm trying to look back, tie things up with the previous discussion. So the form will be my ground state, the spin part orthogonal. Okay, there is one on the left, there's one on the right. They multiply together, you can think about it as a column or a vector with a vector. They are the same. Norm is 1, okay, normalized. So you don't see the spin part anymore, then you have to do this integral. Now this is a single, this is electron 1 kinetic energy seeing the nucleus potential energy. This is the number 2, so these two terms are easy to do. Okay, so it is this kind of term. And if you regard this as the dummy integration variable, in fact, I don't care what the value is, they are the same. I just called it I1, I2. Should be 2I1, okay? They are the same. The more interesting part is this term we discussed last week. It has classical physics interpretation. It is like this bit of charge interacting with that bit of charge due to electron 1 and electron 2 respectively. Okay, that's nice. This is called the direct Coulomb. The symbol I introduced previously is that this is the J integral with states in 1s, 1s. Okay, so that you can calculate out the ground state energy. Now, let's gain something by doing nothing. We are discussing adding two spin half electrons. And we have found what is the S equals 0 combination, which is up down minus down up. If I use a minus linear combination, that will be the S equals 0, 1. But what happened to the triplet state? So that is the question now. There should be 3 of them, right? Because S is 1, MS is 1, 0, minus 1. Now the MS equals 1. Means the projection Z component is 1 times H bar, right? To be formal. Okay, so it's 1 H bar. You have 2 spin half. Leave in the upper cone, the projection is H bar over 2. You have another one. If you want to get the longest Z component, the other one must also leave on the upper cone, okay? And its Z component is also plus H bar over 2, so that the Z component will add together to become longer. All right, follow me? So it is easy to imagine this up situation must be referring to MS equals plus 1 case. Okay, so do you follow me? Similarly, the minus 1 case is also easy. Down, down. Both Z component is minus H bar over 2. They add up, become a longer minus Z component. All right? So we conquered 2 of the S equal 1 state easily. Okay? This will be MS equal plus 1. This will be MS equals minus 1. So what's remaining is this 2 state. If you have 2 things, you linear combine them, you only get 2 things out, right? But we already got 1 with the minus sign. So the only other one is the plus sign. Okay, do you follow me? The plus 1 will give us S equals 1, MS equals 0 state. Okay? That is with the plus combination. Okay, do you follow me? So suddenly, we also have the triplet states. All written out. And we look at the symmetry property. Now, this triplet state, MS equals 1, the longest Z component, is automatically symmetric. Do you see? I interchange the subscript 1 and 2 referring to the 2 electrons. No sign change. So it is symmetric. Down, down is also symmetric. Now, if I use a plus combination, imagine there's a plus sign here, okay, see my symbol. Now, if you interchange 1, 2, the subscript, symmetric. So the conclusion is that triplet spin states are symmetric. Okay, follow me? Therefore, they could go with an anti-symmetric spatial part. Okay, and that will matter in the excited state discussion. So I already explained this. Okay, so I will also explain that. I just explained that this is symmetric. Up, up, down, down is automatically symmetric. So these three together give us the S equals 1 states. There are 3 of them due to MS quantum number, okay? So this one is +1, this one is -1, this one is 0. But the property is that this triplet class, all 3 are symmetric. So summarizing, in one box, we have discussed these 3 triplet states, and in a vector model, it is depicted as this. This one has both vector living in the upper cone, see the 2 arrows, so that the end result add up, okay? In the Z component, this is similar but down, okay? But for this one, the classical picture vector model refers to something like that. You have one living in the upper cone, another living in the lower cone, but they cooperate like this time, okay? So that they live something like rotating distance, okay? But they have the Z component lying down here, okay? So that the Z component is 0, nonetheless, there is something that is circling around. So if you have a angular momentum 1, you would have 3 cones in the vector model, 1, 0, and a -1. So that goes with that vector model sign. Sometimes it's useful, sometimes it's not, but more importantly, you know these 3 combinations. So take home message, 2 spin half, you added up the spin, there is a spin singlet, this combination, you have a spin triplet, these 3 combinations, okay? And if you look at these 2 states, they are very interesting. They are a standard so-called now entangled state. You cannot tell whether one is really up, which one is up, which one is down, because it is a linear combination of these 2 possibilities. We are just talking about the 2 electrons living inside the helium atom. Of course, there's nothing profound for that. But starting, I think, in the 1980s, late 1970s, beyond atomic physics, this state becomes very popular in terms of academic study. So in some experiments, 2 entities, example usually is 2 photons, could be born at the same place, but then they will fly apart in space, okay? And then they are born in this way so that the 2 particles is like one up, the other down, but linear combination like that, okay? Now, when they fly farther and farther apart, if you design some experiment only to measure one particle, whether it's up or down, by quantum mechanics, once you have an answer there, then the other one, until you measure, is still in this entangled situation. But once you measure this to realize, so-called realize it, to go up, this one has no choice. Immediately, it becomes down. And that went all the way back to 1935 to a very famous paper with Einstein as one of the co-authors. That is the famous 1935 Einstein paper with the title something like, Is Quantum Mechanics a Complete Theory? There's one particular point that he did not like this idea, because he was the founder of special relativity, in which it says nothing can travel faster than the speed of light. But in quantum mechanics interpretation, once you realize this to be up, it takes no time. This one must be down. So in Einstein's and his two other authors' viewpoint, there may be someone like picking up a phone call. Now I am up, you must be down. That seems to be violating something that has been traveled faster than the speed of light. That's why in that very famous physical review paper, Einstein regarded quantum mechanics to be incomplete. It cannot be a complete theory. It is a very good theory that can make predictions, but philosophically, it may not be complete. And that started a long, long discussion now, 90 years or so, that involved in the 60s something called the Bell inequality. Someone called Bell suggested that, let me propose some way to test whether quantum mechanics really works the way that Schrödinger proposed, or it is not. Okay, so he derived some very special conditions called Bell inequality that set up the stage for very detailed experimental measurements to test whether quantum mechanics really work as what we think that it is, especially about this collapse of the wave function, basically. Once you have up, you have down, okay? And starting 1970s onwards, there are many, many, and becoming more and more detailed experimental work to test this measurement theory. And I think up to now, the conclusion is that quantum mechanics really works the way as we learn it. We have this wave function collapsing. It takes no time for this entangled state. Once you have up, that is down, okay? And I think soon, very soon, some Nobel Prize will be given to this field. One particular person, I hope that he would get the Nobel Prize, is a French experimentalist. The name I just typed in, okay? Starting the 1970s onwards, he has repeatedly refined his experiment so that someone will challenge some detail, and then he said, next generation of my experiment, I have explained it that there's no loopholes in the experiment, okay? So this is a beginning part of a very fancy thing. And now, your generation is in what is now called the second quantum revolution. The generation starting from 1930s onward up to now is the first quantum revolution, Okay, so the first quantum revolution has led us to all the things that we can use: computer, mobile phone, a lot of things. Okay, semiconductor industry, basically. We use quantum mechanics to understand a lot of the physics of materials, matters, that we are using nowadays. But the second quantum revolution has to do with the remaining properties in quantum mechanics that so far we have not made good use of. There are two particular points. One is superposition in wave functions, okay? Therefore, many ideas about parallel computing using this superposition, thereby quantum computer is an automatically efficient parallel computer, as well as entanglement. These 2 points are at the heart of the second quantum revolution. Entanglement, for example, can be used to do something called teleportation. So I have some secret here. I want to send it or make a quantum fax to the other side, okay? That can be realized by using this entanglement idea. So your generation, I think, will see real applications of this aspect of quantum mechanics. You will encounter more in the future in the more advanced course, okay? But we are very humble discussing the helium atom. Even in ground state, we see this unusual combination. Okay, so this ends this section. The next one is about excited state. Okay, so helium excited state. This section serves 2 purposes. First, we just did the ground state. Why not discuss the excited state? But the second purpose is bigger, okay? I would like to convey why we have alignment in electron spins. And that is the idea behind why do we have magnetic materials, okay? So it is the origin of magnetism. But the physics is hidden inside a discussion on the helium excited state. So now let's see what is the picture that we have. Excited state means one electron in 1s, another electron in 2s. Okay, fine, reasonable. And then, how can we write down something that is legal? All right. Now, let's think about it. We could have, we have 2 states, A and B. They are different now, okay? Now I could have up, down, 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 up, down. Makes sense, right? Okay, so, but the rule is that we must have anti-symmetric 2 electron wave functions. So construct them, okay? So how many of them we can construct? I think now the answer is very explicit and apparent. 2 different states, 1s, 2s. We could construct symmetric space part. Symmetric because I have a plus sign in the middle to go with the spin singlet. The product is anti-symmetric, fine, okay? So the first line is one option. Space part symmetric, spin part anti-symmetric. But in this case, we have more options. The space part can be anti-symmetric because I have a minus sign in the middle, because the states are different. Okay, this is a determinant. All right, now that can go with the spin triplet because this spin part is symmetric. Both will have the total wave function to be antisymmetric. Conclusion on this page, we have 4 different ways to write down possible excited states. Okay, so 1 and another 3. The next question becomes, is this way or that way referring to lower energy? I want the first excited, so the lower one, okay? They may be of the same energy, they may be of the different energy. Okay, let's see, what is it? Therefore, we have a game to do, right? We have to do expectation values. I have the helium Hamiltonian. The 2 options refers to spatial part symmetric, spatial part antisymmetric. The spin part are orthogonal. The Hamiltonian does not depend on spin. Nonetheless, the final answer will distinguish which one will have a lower energy. Now, that is a very important concept. The Hamiltonian that we're going to calculate the energy is spin independent, but we will see that electron-electron interaction will prefer one out of these 2 options. I mean, a symmetric space part or antisymmetric space part will matter. Okay? Now, let's write down. Now, I'm not going to do a detailed calculation for you, but I want you to inspect the expression. We know how to write down the expression. The calculation will be difficult. Now, symmetric space part, Hamiltonian helium atom, symmetric space part. This is the expectation value for this symmetric space part option. You see everything is plus sign, all right? Now, similarly, the singlet excited states, 3 of them, with antisymmetric space part, the only difference is the sign, all right? Now, do you see that there are many terms? Now, there are 3 terms here. There are 2 terms, 2 terms. Multiply them out, there are many, many terms. Do you see? Okay? Now, I schematically try to draw your attention to a particular term. There are many terms that I call sum terms, okay? They involve what we just call I and the direct Coulomb integral. The most funny place or most important place is as follows. I will have terms like, so let me illustrate to you. This, okay, now follow my highlighting point, okay, this one. To go with this thing, okay, then multiply into this thing, and then integrate over everything, okay? Do you follow me? Right? Now, both expression, singlet, triplet, will have this term, but since there is a plus sign, minus sign difference, they will appear with a different sign, okay? So that is what I try to point out here, okay? You will see like plus terms like that I just draw, but minus for the other one goes like this, okay? The integral itself is the same, but due to the symmetry of the spatial part, they have different sign, okay? Now, I have introduced this kind of integral before. First of all, it does not have classical physics interpretation because you don't see any wave function square so that you can interpret as density, probability density, okay? You don't. This is called exchange integral or indirect Coulomb integral, okay? So the question becomes, what is the sign of this integral in helium atom, right? If this is positive with the minus sign, that will be lower energy because it is a plus that positive number, okay? So punchline, it is the exchange integral that determines which option has a lower energy, okay? In different atom, the answer may be different because it is a complicated integral to do. However, for helium, the result is that the triplet state has a lower energy than the singlet state, okay? So this is the exchange integral that I already introduced last week. I just write it out again here to remind you, you don't need to flip back to that page. That is to contrast with the direct Coulomb integral that has classical interpretation. We discussed this in Hartree, and if you include this, this is called the fork term in many-body problems. You may wonder, is there a physical argument that the antisymmetric space part in this situation will lead to a lower total energy? There is one. If you look at the antisymmetric space part, with the minus sign in between, you realize one special effect. This wave function, if the two particles are at the same place, now they are not in the same state, they are just happen to be the same place, the wave function will be zero because of the minus sign. Okay, that means if R1 take on the same value as R2, you see, 1s the same number, or 2s same value, minus that same value, it is zero, okay? But it is not identically zero for all coordinates, no. Only when the two particles happen to be on the same location, the wave function is zero. Interpretation means zero chance to have the two electrons to be in the same location, okay? Now that is good. This space part, that means avoid the electrons to be too close to each other. It's good because we have the Coulomb repulsion. If the wave function already tried to avoid them to be too close to each other, this contribution of the Coulomb repulsion will be reduced. When R1 equals R2 will be very big, right? Close to it, but it is positive, okay? So here we have a way to understand what this symmetric, antisymmetric space part is doing, okay? It automatically avoids the two electrons to be too close to each other, okay? So what we found is the following. We discussed the ground state. The first excited state is this triplet state, now slightly lower energy. And the one with the symmetric space part that go with the spin trip singlet, okay, is a slightly higher excited state, all right? Here, I also introduced the same term symbols that we introduced in the hydrogen discussion. And that leads us to a simple way of understanding why it is so, right? Avoid the two electrons to be too close to each other, okay? And that is also related to something called the Hund's rule. Hund's rule is more general than what we just discussed. For example, a question is, when we have bigger atoms, we have two electrons to put into the 6p state. How to put it? Should we put one up and other up, say px,py, or we pair it up in px? Which one will has the lower energy? Okay. Now it turns out that you can think, right, that this is like spin symmetric. Therefore, spatially will be antisymmetric. The electron avoiding each other, that will be a lower energy state. Indeed, this is the way to fill electrons in. This is one of the three rules summarized as Hund's rules in physics and in chemistry. Hund's rule told us how to put electrons into single particle states. For example, d states, right? There are 10 d states. If you have 4 electrons, what do you do? Okay, do you use up down into one, another up down, and then run out of electron, or you try to do up 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 up, or down 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 down, right? They are equivalent. Okay, Hund's told us that the lower energy will be achieved by up 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 up, okay, or down 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 down, but don't pair it up too soon. Okay, that is what Hund's rule does. I don't intend to discuss Hund's rule in detail here, okay? But you can now realize what these rules have to do is actually keep on doing quantum calculations, right? Now, for example, if you write this in your mind, if you think about this in your mind, you have a special Slater determinant. Then you can do the Hamiltonian calculation, right? Okay? But you have to solve this Hartree equation first for the single electron state and then do the expectation value. Now, if you want to compare energy, then you have to write down another Slater determinant for this up-down situation. You redo the calculation, then you have two energies to compare. Which one is lower, okay? Of course, you don't want to keep on doing it every time, and therefore, Max Born, you know, the Born interpretation, the big famous quantum guy, Hund's was his student. So Hund's did a lot of this calculation, and at the end, summarize it into 3 rules that tells you you don't need to do the calculation again and again. Follow my rule, you will get the lowest energy state. Okay, that's what Hund's rule means. Okay, so this is what Hund's rule told us. Okay, and the term symbol, I already introduced it in hydrogen atom. This page is just to remind you what they are. Okay, again, you don't need to flip back to hydrogen. Okay, so let me just use 1 more minute to hint at something big. You see, in helium, what we found is that the triplet state is slightly lower energy than the singlet excited state. But we understand that the triplet state has up, up, or down, down, or up, down, plus down, up. Okay? In general, the 2 spin tend to align. The singlet, they exactly cancel. They tend to anti-align. Okay? So somehow, in this simple discussion, we see that the Coulomb electron-electron repulsion selects or prefers spin to be aligned in this helium atom case. Okay? And that is a big, big piece of physics, because that is the beginning of the understanding of magnetism. We are not thinking in terms of the dipole magnetic dipole moment, they interact like a dipole interaction in your E and M book. No, 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 it's not that. The actual interaction is mediated by Coulomb interaction. The spin part comes in through the requirement that the multi-electron wave function must be antisymmetric. And then some preference will come out where the spin triplet is lower energy, spin singlet is lower energy. That will that will force this material, the spin in the material, to be aligned or anti-aligned. In fact, we see both types of materials. When the spin tend to align in a material, it is called ferromagnetic, ferromagnetic, 鐵磁性啊，鐵磁性. If spin tend to anti-align with the laboring one, okay, anti-align, it is called antiferromagnetic, 反鐵磁啊，反鐵磁性啊. In fact, we see materials with these two types of properties. Okay, so I will stop here today. Next time, I will fill in a little bit about this story of the origin of magnetism, because magnetic problems are again at the forefront of many condensed matter physics problems. Okay, so I will start here next time, and then we will discuss the periodic table and end this module about the physics of atoms. Okay, so I see you next Tuesday. Bye-bye.